Assalamu alaikum dear students. My name is Salman Amin Malik and I am your instructor for the course Linear Algebra whose code is Mth231. I did my PhD from University of La Rochelle, France, and I am here to teach you the course Linear Algebra. If you see the title of your course, it's Linear Algebra. It consists of two letters, linear and algebra. Algebra is a big branch of mathematics in which we study different spaces and different structures. But in linear algebra, as it is evident that we are going to study about something which are linear. Linear comes from the line, straight line. You know that straight lines in 2D and 3-dimensional space. So we are going to study the linear equations in which the variables have power 1 and more than one equation. We are going to study what we call the system of linear equations. We are going to study in this course the system of linear equations as well as their properties, their solutions, and some spaces and some other facts which you will see in the course contents of the course. So let's go to the slide and see what are the course contents of the linear algebra, which is Mth231. The course linear algebra can be divided into three major parts. In the first part, if we go to the slides, in the first part we are going to study the system of linear equations and some related concepts which are the row reduction and echelon forms of the system of linear equations. Then we are going to study the vector equations of the system of linear equations, the matrix equation, solution set of the system of linear equations, and some transformations. Transformations are some functions. Please don't worry about these terminologies. These terms we are going to discuss in our future lecture. So you need not to worry if you don't know about these technical terms. These are the course outline which I want to give you before starting the course. So in the first part we are going to study the system of linear equations. In the second part, which is more concerned about the matrix operation, and we are going to study the system of linear equations by using the terminologies of matrices. Then we will study the inverse of a matrix, characterization of invertible matrix, matrix factorization, and their applications. And of course, we are going to study the determinants and their properties. The part 3, which is the major part of your course, is about the vector spaces. What are these spaces? For a layman, a space in mathematics is just a set of elements, set of members which satisfies certain conditions. What are these conditions? We are going to discuss in this course, and we are going to study different properties as well as we are going to study the solution of the system of linear equations in certain spaces. So the third part, which is the major part of your course, is about the vector spaces, their subspaces, bases, null spaces, column spaces, coordinate system, and some related topics which are eigenvectors, eigenvalues, and some other things. So once again I am saying you that don't worry about these terms. These are technical terms which we are going to discuss during this course. Okay, now I am going to tell you about the book which I will follow during these courses, this course, Linear Algebra. So the textbook which I will follow is written by David Seeley, and its title is Linear Algebra and its Application. And we are going to follow the 4th edition of this book, which is published by the Edison Wesley and which have ISB number given by this one. This is the textbook of your course which I will follow rigorously. The ISB number for each book is a specific number assigned to that book. If you put that number in Google or some other search engine, you will get all the information about that book, which is written by the David Seeley. There are some other recommended books, which are two. The one is written by the Gilbert Strong. He is a professor at MIT, Introduction to Linear Algebra, and its 4th edition, which has been published by Wesley Cambridge Press and which has ISB number given by this one. The third book, which you can use as a reference book, is written by Lee W. Johnson, R. Dean Rees, and Jimmy T. Arnold, whose title is Introduction to Linear Algebra, 5th edition, and the publishers are Addison Wesley with ISB number this one. So the textbook we are going to follow rigorously, and the reference books you can use for the solution of your assignments, your quizzes, and so on and so forth. You can consult the reference books. The textbook is available in Pakistan easily. You can find the textbook Linear Algebra and its application, 4th edition or 3rd edition, it doesn't matter. There is not a big difference between the 3rd edition and the 4th edition, written by David Seeley. So you can have this book, the textbook, and the reference books, of course, are available in the market as well as in the good libraries. You should have the textbook at least. Next, I'm going to tell you about the assessment plan of the course during the course. During the course, there will be 4 assignments and 4 quizzes. There will be 1 sessional, what we call the first sessional, the second sessional exam, and the final term exam. So you have 4 assignments, 4 quizzes, first sessional exam, second sessional exam, and your final term exam. Let's see on the slide what are the weightage of these assignments, quizzes, and some other assessment. So there will be 4 assignments, as I told you earlier, and the weightage of the 4 assignments will be 10%. There will be 4 quizzes and the weightage of the quiz will be 15%. The first sessional exam, which normally will be after 10 lectures, will have a weightage of 10%. Second sessional exam will have a weightage of 15%, and the final exam will have a weightage of 50%. So it comes out to be total 100%. Okay? Before I formally start the course Linear Algebra, let me put some physical examples from the real world, which when we try to solve these physical models, these lead to the system of linear equations. And if we have the solution of such a system of linear equation, then we have the solution of our physical world problem. The first problem is the mass balance problem, in which you have a wedge and you have a rod. You have 3 different objects. You know the mass of one object, but the mass of the 2 objects is unknown, and we want to determine the masses of these 2 unknown objects. So let's go to the slides and see the figure corresponding to this problem. So this is a wedge and we have a rod here, this one. We have 3 different objects, H, C, and 2. The 2 object of mass 2 has 2 kilogram mass, and these 2 objects have unknown masses H and C. So whenever an object is placed here on the rod, it tries to turn the rod in this direction. For example, this mass will try to turn this rod into this one. If our rod is in a balanced position, अगर ये हमारा rod जो है ये balanced position पे है, it means the turning effect of this mass equals the turning effect, sum of the turning effect of this H, object H, and object C. Now, how to calculate the turning effect? The turning effect is calculated by the mass of the object and the distance from wedge this to the center of the gravity. For example, for this object for which we know the mass is 2 kilogram is 50 for this particular figure. So if I am going to write down the equation, mass balance equation for this first figure, then this object of 2 kg try to turn the rod into counterclockwise, whereas these two masses try to turn the rod into anti-counterclockwise. So the mass equation, mass will be balanced by this. For this figure we have this linear equation, which is the 40h. 40 is the distance of this object h from the wedge to the center of the gravity, 40, and h is supposed to be the mass of the object. We have 40h plus 15 is the distance of the object c from the wedge, and we suppose that mass of the object, this object, is c. So 40h is the turning effect due to the mass object h, and 15c is the turning effect due to the object, this object whose mass is supposed to be c, and this is equals 2 into 50, which is turn out to be 100. So this is the first equation we have for this figure. Similarly, we can have the different positions of these three object masses, and we have another equation. How to interpret this equation? We have now the clockwise turning effect is given by this object c, and its turning effect is 25 into c, which should be equal to the 2 into 25, which is the turning effect due to the object of mass 2, which becomes 50, plus the turning effect of due to the object h, which is 50 into h. So this is the physical real world problem in which we have to determine the masses of two objects, which we suppose that the mass of the first object is h and the mass of the second object is c. And we have used the mass balance equation, and we got two equations with two unknowns. So if we have to find out h and c, the masses of h and c, we have to find out the h and c by solving these two equations. This is a simple and very interesting example, physical world example, which leads to the solving, whose solution leads to the solving the system of linear equation. Apart from that, linear equation or the system of linear equation or the linear systems arise in many physical problems. For example, in linear programming, I have mentioned some of these in the slides. In linear programming, we have the system of linear equation that may be 100 equation, million equation, 10,000 equation with several variables, 10,000 variables, and we have to solve these system of linear equation. Of course, a human being can't solve a system of linear equation with, let's say, 10,000 equations and 10,000 variables. These are the jobs of computers. So in linear programming, the airline industry, for instance, employs linear programs that schedule flight crews, monitor the locations of aircraft or plan the varied schedule of the support services such as maintenance and terminal operations. Apart from that, system of linear equation has been used in electrical networks. Engineers use simulations, software for designing of microchips, and etc. So there are many physical problems whose solution lead us or ask us to find out the solution of the system of linear equations. There are some terms which has been used while I am explaining the physical world problems which arise to the solution of the system of linear equation. For example, the first thing is, which equation is the linear equation? Are there any other equations? Yes, of course. There are linear equation and some other equation which we call the nonlinear equation. So let's go to the slide and see which are the linear equations. I have mentioned here on the slide that the two equations. The first one is here x1 and x2 are the variables. I hope that you know the variables. The variables are the symbols which can have the values from a certain set. For example, x1 and x2 are variables because x1 and x2 can assume any value from the set of real numbers. So the variables in this example, the variables have power 1. If we see here in this equation, this equation reads 3x1 minus 5x2 equals 4x1. Whenever the variables have power 1, we will say that this is a linear equation, and we should not have any term in our equation which involves the product of two variables. So the first equation, this one, is a linear equation, and let's see this equation, which is x1 minus square root of 5 x2 equals 4x2 plus 5 square root of 5. This is the constant term. This is the linear term in variable x2 because x2 has power 1. This is also linear term, and this is also a linear term. So this equation is also a linear equation. Both these equations, which are here and here, are linear equations and can be simplified to these two equations. Of course, we can do the simplification. For example, this equation has been obtained by simplifying this equation. We take the 3x1, the other side of the equality symbol, and it becomes x1, 4x1 minus 3x1, which turns out to be x1, and we take this also to the other side of the equality. So ultimately we have x1 plus 5x2 equals 0. Similarly, we do the simplification for this one. Let's consider some other equations which are nonlinear or which are not linear. Consider these two equations which are here and this equation. This equation, the first two terms are linear because the variables are as usual x1 and x2, and both have the power 1. The first term has the power 1, second term has the power 1. But this third term, which is in red, is a term which is obtained by the multiplication of two variables. So this is the nonlinear term, and we say this equation is not linear. Similarly, for the second equation, in this case, all the terms first, second, third, these are linear because the variables have power 1, and this term, which is square root of x2, has power of variable x2 as 1 by 2, which is not 1. Of course, this equation is not a linear equation. So let's define a linear equation with n variables, where n is any natural number. N could be 2, n could be 3, n could be 10,000, n could be any number, any positive number. So a linear equation in the variables x1 up to so on xn has the form this one, where a1, a2, a3 up to so on an are known as the coefficients of the variables x1, x2, x3 and xn. These coefficients of the variables are real numbers or complex numbers, and these are non-numbers. And d is also a real number. So this is an equation with n variables. We have the variables x1, x2, x3, so on and so forth, xn, and n could be any positive number, natural number. N could be 1, 2, 10, 100, 50, 70, or whatever. Now let's see in the next slide what are the system of linear equations. Of course, by name we know that the system of linear equations mean that we have more than one linear equation, and these equations could be in 2 number, in 3 number, in 4, 10, 15, maybe 10,000, so on and so forth. So the system of linear equation is the combination of linear equation, or we combine all the linear equation. Let's see the examples. In the first example, we have 2 equations and 3 variables. The variables are x1, x2, x3, and this is the first equation. And we have these second equation with variable x1, x2, and x3. So this is a system of linear equation which has 2 equations and 3 unknowns. Let's consider another example. This is the example in which we have the 4 variables x1, x2, x3, and x4, and we have 3 equations 1, 2, and 3. So all 3 equations involves the 4 variables. So this is a system of linear equation with 3 equations and 4 unknowns. Now I am going to define generally with m equations and n variables, a system of linear equation which has m equations and n variables. So a system of linear equations with m equations and n variables is defined as where a11 is the coefficient of the x1. Here we have the variables x1, x2, so on and so forth, xn equals d1. This is the first equation. For the second equation, I have the same variable but with the different coefficients. A11 is known as the coefficient of the x1 in the first equation. In fact, how we read it? We read it A1, the first equation, the first variable, A11. So by the index of each coefficient, we can know the position of the variable where it is situated. For example, A2n means this is the coefficient of the variable xn in the second equation. For example, A22 means this is the coefficient of the variable x2 in the second equation. The first component or subscript of the coefficient of the variables is always corresponding to the number of the equation, and the second subscript correspond to the variables for which it is the coefficient of the variable. For example, am2, what does it mean? इसका मतलब है कि am2 is the coefficient of the variable x2 in the mth equation. So this is a system of linear equation which have m equations and n variables. Now let's go to the further and start with simple examples with 2 variables, and you know that the linear equation with 2 variables always represents a straight line in 2-dimensional space. Whenever I say 2-dimensional space, it means a 2D plane, 2-dimensional plane which has been formed by 2 perpendicular lines which we call the x-axis and the y-axis. So let's go to the slide. We have these 2 equations. In fact, this is a system of linear equation with 2 variables and 2 equations. For the first equation, I call it the L1. The second equation, I call it the L2. As I told you earlier, that the linear equation in 2 variables always represents a straight line. Let's go and try to plot the L1. How to plot L1? किस तरह L1 को plot करते हैं? For the plotting of a straight line, we need 2 points in the plane. How we get the 2 points? We take x2 equals 0, and we are getting the values of the x1 for L1. So whenever our variable x2 is 0, then our x1 has the value -1. So we are having a point which is here in this figure when our x2 variable, which correspond to this axis, and x1 correspond to this axis. Normally we have here x-axis and y-axis, and in this case we have x1 here and x2 here. It's the same thing. So we have a point whenever we have x2 0, then we have x1 equals -1. So we have this point and another point. Another point is obtained by taking x1 equals 0. Whenever x1 equals 0, we have x2 equals half 1 by 2, which is this point, and we can easily join these 2 points and get the straight line, which is the graph of this equation L1. This is the L1. Similarly, we plot the L2 and we see that these 2 lines L1 and L2 intersect at a point. This is what we call the solution of the system of this linear equations. Of course, we know that whenever 2 lines intersect, it's always intersect at a point and the point is unique. So our system of linear equations will have a unique solution in 2 variables and 2 equations if the graphs of these 2 equations, which are the straight lines, intersect at a point. And of course, if the lines intersect, then they intersect at a unique point. एक यूनिक पॉइंट पे जो है लाइंस इंटरसेक्ट करती हैं. इस फिगर में जो है आपका ये यूनिक पॉइंट है, विच इज द सॉल्यूशन ऑफ द दिस सिस्टम ऑफ लीनियर इक्वेशन. सो दिस इज द फर्स्ट पॉसिबिलिटी दैट a system of linear equation can have only one solution. Let's go to the next slide and explore the other possibilities. I have written here 2 examples. The first one is given by this one, and of course once again मैंने यहाँ पे denote किया L1 and L2 से these straight lines को. The A system of linear equation, which is denoted by A, the lines are plotted here. These 2 lines are parallel. Of course, these 2 lines will never intersect because these 2 lines are parallel. So we can say that these 2 lines or the system has no solution. Why? क्योंकि ये 2 lines कभी भी intersect नहीं करेंगी. For the system of linear equation with 2 equations and 2 unknowns or 2 variables, what is the geometry of solution if it exists? If it exists, then the lines must intersect. So these 2 lines are parallel, they will never intersect, and our system A does not have a solution. So we have the 2 possibilities, whether a system of linear equation can have a unique solution or a system of linear equation can have no solution. Let's see the third system of linear equation in 2 variables with 2 equations. These 2 lines, if I plot these 2 lines, in fact these are not 2 lines, it's only 1 line. These 2 lines are overlapping lines, what we call the overlapping lines. So every point on one line also lies on the other line. So we have infinite many solutions. It's the possibility that we have infinite many solutions for the system of linear equations, such as this is the example in 2-dimensional space, or the system of linear equation with 2 variables. So let's summarize what we have learned from these 3 systems of linear equations. The first system of linear equation have a unique solutions, and the geometry of the lines were that the lines were intersecting. The second system of linear equation has no solution, and the geometry of the lines were that the lines are parallel. And the third system of linear equation has infinite many solutions, and the geometry of the equations was that these were 2 overlapping lines. Now the question arises, we have considered the system of linear equations with two variables and two equations. Can we have the same phenomena for any system of linear equations in which we have different numbers of variables and different numbers of equations? Let's see on the slide. So this is the remark which I have explained to you. For a system of linear equation with two variables and two unknowns, we have three possibilities. System has a unique solution, infinite many solutions, and no solution. Let's do some example in which we have to check whether a given set of numbers is a solution of a given system of linear equation or not. Let's go to the slide and see how to solve this one. This is the order pair, example 1. The order pair -1, 5 is a solution of this system. This is the system of linear equation 2 by 2. How to check this one? This is the order pair. It means our x1 have value -1 and our x2 has value 5. Whenever we substitute or put these values of x1 and x2 in our equations, both equations should satisfy. Let's put x1 equals -1 and x2 equals 5 in the first equation, and we see that the answer is -3 plus 10, which is 7. The first equation is satisfied. Let's check out the second equation. +1 plus 5, which is 6. So -1, 5 is a solution of this system of linear equation. In contrast, 5 minus 1 is not a solution of the same system of linear equation. What does it mean, 5 minus 1? It means that we have x1 equals 5 and x2 equals -1. If we put x1 equals 5 and x2 equals -1, then we will have 15 minus 2, which is the LHS will give us the answer 15 minus 2, 13 equals 7, and everybody knows that 13 is not equal to 7, so the first equation is not satisfied. So -1, 5 ordered pair is a solution of this system, whereas 5 minus 1 is not a solution of this system of linear equation with two variables and two unknowns. Let's see another example is 3, 4 minus 2 is a solution of the following system. If this is a solution, if we take x1 equals 3, x2 equals 4 and x3 equals -2, then each equation must satisfy. 5 3s are 15, minus 4, that turns out to be 11, and -4, 11 minus 4 equals 7. So the first equation is satisfied. 3 2s are -6, 6 we have to put x2 equals 4 here, 6 4s are 24, and we have -18. We have 24 minus 18 and 6. So LHS equals 0, RHS equals 0. Let's check the third equation. We have the value of x1 equals 3. We have here -21. We have here plus 5 4s are 20. So this turns out to be -1 and minus, that will be 6, -6, and it turns out to be -1 and plus 6, which is 5, is not equal to -7. So this is not a solution of the system of linear equation because the third equation is not satisfied. If we put x1 here, it's -21. If we put 4x2 here, x2 equals 4 here, we have 21. It turns out to be -1. And if we put -2 here, we have here +6. +6 minus 1 equals -5, which is not equal to -7. So this is not a solution of the system of linear equations. Now we are going to define the solution set of a system of linear equation for a general system of linear equation. A system of linear equation with m equations and n variables, which we have already discussed, could be written as here, has the solution S1, S2, Sn if that n tuple, we called it the n tuple because it has n different real numbers, S1, S2 up to so on Sn, is a solution of all the equations in the system. As we check in the previous examples that we call a solution of a system of linear equation if all the equations are satisfied whenever we put the values of the x1, x2, so on and so forth into each equation of the system of linear equation. So this is the how we define the solution of the general system of linear equation with m equations and n unknown. So let's summarize what we have learned. I have written here, recall, for a system of linear equation with two variables and two unknowns, we have three possibilities. System has a unique solution, system has infinite many solutions, and system has no solution. Let's define the terminologies of consistent system and inconsistent system. A system of linear equations we call it consistent if it has a unique solution or infinite many solutions. It means the solution of the system of linear equation exists, and we call it that the system is consistent. A system of linear equations is known as inconsistent if it has no solution. Now I have put a question, can a system of linear equation has only two solutions or only three solutions, or let's say 10 solutions, 100 solutions? The answer is no. There are only three possibilities for each system of linear equations. Whether the solution is unique, system has infinite many solutions, or no solutions. Now a question arises, how to find the solution of a system of linear equations? Before we study an algorithm in which we will calculate the solution of the system of linear equation, I will define some terminology about the matrices so that you will easily follow the method or algorithm for the solution of the system of linear equations. So just I am recalling you what is a matrix. A matrix is a rectangular array of numbers. A matrix is an arrangement of numbers. What type of arrangements? For example, I have given one example. This is a matrix of order 3 by 4. What does it mean, the order? Order means, since I told you that matrix is an arrangement of numbers, this is an arrangement in which we arrange the numbers in rows. The first rows, for example, in this matrix we have this first row, and the first entry of the first row is 1. The second entry of the first row is 0, and we read it as the first row and first column. These are the rows of the matrix, 3 rows. This matrix has 3 rows, and these are defined, the vertical entries are defined as the columns of the matrix. So these are the columns, and this matrix, which is here, has 3 rows and 4 columns. 1, 2, 3, 4 columns. And each entry is located as compared to the row, in which row this entry is and in which column this entry is. For example, this entry is known as 1, 1 because it is situated at first row and first column. This entry is known as 1, 2, first row and second column. For example, this entry is known as second row and fourth column. So this is the entry whose position is second row and fourth column. For example, this one has third row and second columns. So the position of this entry, this arrangement, in this arrangement is third row and second column. So this is a matrix having 3 rows and 3 columns. The order of a matrix is defined as the number of rows into the number of columns, and we read it as this is a matrix of order 3 by 4. Here we have 4 columns. For example, this is a matrix in which we have 3 rows and 1 column. This is usually known as a vector also. Here is another example of the matrix in which we have 2 rows and 3 columns. So the order of the matrix will be 2 rows multiplied by 3. For this matrix, the order of the matrix is 3 multiplied by 1. Let's go to the next slide. So we want to study how to solve the system of linear equations. We have this particular type of system of linear equations, and before we start how to find out the solution of a system of linear equations, let me tell you some terminology. We have a system of linear equations with 3 unknowns and 3 equations. The matrix, this one, which is in fact, if we observe that, what is that matrix? This is the matrix of coefficients of the variables x1, x2 and x3 in our system of linear equations. For example, the first entry is the coefficient of the variable x1 in the first equation, which is 1. The second entry is the coefficient of the variable x2 in the equation 1. So in each row we have the coefficient of the variables x1, x2 and x3. 1, 1, -2 and 3. In the second row of the matrix we have the entries of the second equation of the system of linear equations, 0, 2, -8, and in the third row we have the entries in the coefficient of the variables x1, x2, x3 in the third row, -4, 5 and 9. So this is the matrix we have formed by collecting the coefficients of the variables in our system. Such a matrix is known as the matrix of coefficients of the system of linear equations. Now if we add one column, which is B, normally we call it B, 0, 8, -9, to this coefficient matrix, we obtain this matrix which is written here. You can see that the difference between these two matrices is only that in this matrix we have added one column which corresponds to the right hand side of the system of linear equations, which is 0, 8 and -9. This is known as the augmented matrix of system of linear equations. So these are two very important matrices corresponding to the system of linear equations, and we are going to work with such type of matrices. The first matrix is known as the matrix of coefficients, in which we collect all the coefficients of the variables in our system of linear equations. If you notice that if these columns are the coefficients of the variable x1 in our system of linear equations. For example, for corresponding to x1, we have the coefficient 1, 0 and -4. So the first column is corresponding to the variable x1, the coefficients of the variable x1. The second column corresponds to the variables coefficient of the x2 in our system. You can see that -2, 2 and 5. And augmented matrix is just we have added the right hand side to the matrix of coefficients as a column, and we have this augmented matrix. The size of a matrix, whether coefficient matrix or augmented matrix, tells us about the system of linear equations, that how many variables are there and how many equations we have. Let's see this example. For this system, the matrix of coefficient is For the x1 coefficient we have 0, 1, 1 by 3. For the x2 coefficients, there is no x2 coefficient in equation 1, so we have 0, 5, 2. For the x3 coefficient, we have in the first equation 3, minus 2 and 0. So matrix of coefficient is this one for this particular system of linear equation. And the augmented matrix, in which the augmented matrix has been obtained by adding one column to the matrix of coefficient, and that column is correspond to the RHS of right hand side of our system of linear equation, which is 9, 2 and 3. 9, 2 and 3. So the augmented matrix is given by this one. We have the matrix of coefficient and the right hand side of the system of linear equation. So we know how to write down the matrix of coefficients and augmented matrix whenever we are given a system of linear equation. Let's see another example. If the matrix is the augmented matrix of a system of linear equation, write down the system of linear equation. So this matrix is the augmented matrix of the system of linear equation, and we have to write down the system of linear equation. As we have decided, the first column represents the coefficients of the first variable, let's say x1 in our system. The second column represents the coefficients of the, let's say, variable x2, and third column is the coefficients of the variable x3. So by this augmented matrix, and the last in the augmented matrix, we always have the last column as the right hand side of our system of linear equation. So the information this augmented matrix gives me about the system of linear equation is that this system of linear equation has 3 equations and 3 unknowns. The first equation can be written as 2x1 plus 0 x2 minus 2x3 equals 5. So this is the first equation we have. 2x1, and because it is 0 coefficient, I didn't write it, minus 2x3 equals 5. Similarly, we can write the other 2 equations, and from the augmented matrix, we can write down the system of linear equation. Now let's go to the next slide. How to solve the system of linear equations? We are going to study the Gauss elimination method for getting the solution of the system of linear equation. For this example, solve the system of linear equation, which is the same linear equation we have discussed in the previous example. The augmented matrix for this system of linear equation is written here, and I hope that every one of you can write down the augmented matrix for a given system of linear equation, and you can check that the augmented matrix is this one. Now if we have to solve this one, what we are going to do? The first transformation rewrites the system of linear equation by interchanging the first and third row. Why we are doing this? There is a reason behind it. So first of all, we will try to go through the steps, then I will tell you the logic why we are doing it. So the first step is swap row 1 with row 3, and there is no change in the system of linear equation because I am just swapping the equations. Is there any difference if I swap any 2 rows of a system of linear equation and get another system? Of course, there is no difference. It's just writing the equation first and second or third or last, to which I am swapping the system of linear equation. So the first one, I am going to swap the system of linear equation. The similar operation I will do with my augmented matrix. So I will also swap the first row with the third row in my augmented matrix. So my first row of the augmented matrix will become this one, and the third row of my augmented matrix will become this one. The second transformation is that I rescale the first row by multiplying both sides of the equation by 3. So I multiply equation, the new equation 1, which is this one, by 3 and get a new equation, and the remaining two equations remains the same. So multiply row 1 by 3. I did same with the augmented matrix. So the operations with the system of linear equations and the augmented matrices go side by side. The third thing is we multiply both sides of the first row by -1 and add that to the second row and write the result in as a third row. So I multiplied the first row with -1 and add to the second row. My new equation will be, system of linear equation will be like, why we did this one? Because I want to make 0 coefficient of the x1 in the second equation. So the same thing I did in the augmented matrix. So this is the augmented matrix. Now from the bottom equation, from the third equation, I can have the x3 equals 3. And I can put this value of x3 into the second equation, which is this one. And I get the value of the x2, which is 1. For getting the value of the x1, I have the value of x3 and x2, so I put value of x2 and x3 in equation 1, and I got x1 equals 3. So we are able to find out a solution of the system of linear equation, which is x1 equals 3, x2 equals 1, x3 equals 3, which is a unique solution of the system of linear equation. The steps which we follow are known as the Gauss elimination method. In fact, what is that algorithm? In this algorithm, we eliminate the variables from the system of linear equations. And what we have done, the operations by eliminating these variables, we do the same operations with the rows of our augmented matrix. Let's see another example for the solution of the system of linear equation. And before doing this, we should verify whether the solution, which is x1 equals 3, x2 equals 1, x3 equals 3, is a solution of the system or not. And we all know that how to verify this one. In this slide, I am verifying that this solution, in fact, is a solution of the system of linear equation. So how we verify? We put these values of x1, x2 and x3 into system of linear equation and see whether these equations are satisfied or not. So we can easily check that this is the solution of the system of linear equation. All equations of the system of linear equation are satisfied, and hence the set is a solution of the system of linear equation. Let's do another example in which we try to solve the system of linear equations by Gauss elimination method. So we have this system whose augmented matrix is given by this one. Augmented matrix has the rows 1, -2, 1, 0, which is the first row. 1, -2, 1 are the coefficients of the variable x1, x2 and x3, and 0 is the RHS of the right hand side of the first equation, so on and so forth. So in the first position of the augmented matrix we have 1, and if we want to eliminate, we see that there is no x1 in the second equation, and we have to eliminate this x1 from the third equation, which is here. Keep x1 in the first equation and eliminate it from the other equation. This is the process of the elimination. So what we have to do, 4 times of equation 1 and we add to the equation 3. It will eliminate the x1 variable from the equation 3, and ultimately we have this system, and the same thing we do with the augmented matrix. The next procedure is we want to make the coefficient of the x2 variable in equation 2 as 1. So we multiply equation 2 by 1 by 2 in order to obtain 1 as the coefficient for x2. So we do here multiply second equation by 1 by 2, that will make the coefficient of x2 1, and we do the same with the augmented matrix, that we divide the row 2 of the augmented matrix by 1 by 2. What we have to do next? Use the x2 in equation 2 to eliminate the minus 3x2 in equation 3. Of course, we have to multiply the equation 2 with 3 and add to the equation 3, and we have this solution. Our equation number 3 will become this one, and we do the same thing with our augmented matrix, that we multiply row 2 by 3 and add to the third row, and the augmented matrix will become this one. This is a particular type of matrix in which all the entries below the diagonal are 0, and we call such a matrix tridiagonal matrix. Next, we want to make zeros these red entries. Although we can have the solution of the system of linear equation from here, but we want to make these entries of the matrix and these entries 2x2, x3 in first equation minus 4 x3 in the second equation as 0. So we will do two operations, 4 times multiply equation 3 and add to equation 2, and multiply equation 3 by minus 1 and add to equation 1, that will make the coefficients 0. The coefficients minus 4 and the coefficients of the x3, that will make 0, as we have ultimately here. The coefficients of x3 in equation 2, the coefficient of x3 in equation 1 are disappear. So we do the same with the augmented matrix. Next, we have to make this one, the coefficient of the x2 variable in equation 1 as 0. So we multiply the equation 2 by 2 and add into the equation 1. This leads to this system, and our augmented matrix become this one. So the solution directly we don't need to use the back substitution. What is back substitution? Back substitution is that we have x3 variable here, and we put the value of the variable x3 in equation 2, and we get the value of the x2. And then for getting the value of x1, I put the value of x3 and x2 into equation 1. That is known as the back substitution. We are putting back the values of the variables in the other equations for getting the values of the preceding variables. By doing this, by making these red entries 0 in the system of linear equation, we directly have the solution, which is x1 equals 29, x2 equals 16, and x3 equals 13. You can verify that this is a solution of the system of linear equation. In fact, in the next slide, I have written the same system of linear equation, and I am verifying whether this is the solution of the system of linear equation or not, which is x1 equals 29, x2 equals 16, and x3 equals 3. So I put these values of the x1, x2 in my system of linear equation, and I see that you can verify that these equations are satisfied. What is the geometry of solution of system of linear equation with 3 unknowns and 3 equations? You have to remember that any equation, linear equation in 3 or less than 3 variables always represents a plane in 3-dimensional space. What are the 3-dimensional space? In the 3-dimensional space, we have 3 reference axes: x-axis, y-axis, and z-axis. So all these equations on the slides represents a plane, and if we have a unique solution for the system of linear equation, it means that all these three planes intersect at a unique point, as you can see in this figure. We have this plane, green plane, blue plane and yellow plane, and all these three planes are intersecting at a unique point. So let's do another example in which we have to determine if the following system is consistent or inconsistent. Remember that a system is said to be consistent if the solution of the system of linear equation is unique, or the system of linear equation has infinite many solutions. So this is the system of linear equations whose augmented matrix is written here, and we do the same thing as we did previously, but I am doing the same thing with augmented matrix. That's why in the previous slides I take the system of linear equations and I do the process of elimination, and I make the same operation with my augmented matrix. From now onward, I will do the elimination process with my augmented matrix. You have to learn that in augmented matrix, you have the coefficients of the variable involved in the system and the right hand side of your system of linear equations, as we have learned earlier. So to obtain an x1 in the first equation, interchange rows 1 and 2. This will always happen that we will make our first row such that the coefficient of the first variable is non-zero. So we make an interchange of row 1 and 2 in the augmented matrix, and we got this matrix, just the interchange of the two rows. To eliminate the 5x1 term in the third equation, add minus 5 by 2 times row 1 to row 3. And row 3 has been replaced by the answer we are getting by multiplying minus 5 by 2 to R1 and adding to the R3. So I multiply this row by minus 5 by 2 and add into this row. So the answer has been written in the third row, which is 0, minus 1 by 2, 2 and minus 3 by 2. So this makes the coefficients of x1 in my third equation as 0. Next I have to eliminate the minus 1 by 2 x2 term from the third equation. So I will add 1 by 2 times row 2 to the row 3, and ultimate answer will be 0, 0, 0 and 5 by 2. So my system is in a triangular shape, or my augmented matrix is in a triangular form. So I am going to write down the equations corresponding to this augmented matrix. So the variables are x1, x2 and x3, and this is the RHS of my system. So 2x1 minus 3x2 plus 2x3 equals 1 is my first equation. x1 has 0 coefficient, so x2 minus 4x3 equals 8 is my second equation. x1 has 0 coefficient in the third equation, x2 has 0 coefficient in the third equation, and x3 has 0 coefficient in the third equation. So ultimately I am having 0 equals 5 by 2. What about this one, 0 equals 5 by 2? Is it true? Of course it is false. So this is absurd. Everybody knows that 0 is not equal to 5 by 2. It means that our system has no solution, or our system is inconsistent. Remember that we have defined that a system of linear equation is consistent if the system of linear equation has a unique solution or infinite many solutions. we tried to solve the system of linear equation and we reached 0 equals 5 by 2. One of the equation gives us this 0 equals 5 by 2, which is of course not true. So we will conclude that our system of linear equation is inconsistent, and geometrically it means the three planes corresponding to the three equations in our system of linear equations don't intersect at a unique point, as you can see in this figure. The intersection of two planes is this blue line, and the intersection of other two planes is another line which is below these planes. They never intersect at a unique point, and we don't have a solution of the system of linear equation. Let's do another example. For what values of h and k is the following system consistent? We have to find out the values of h and k. H and k are unknowns, which are the right hand side of your system of linear equations, 2 by 2. And remember that the geometry of these equations are straight lines. So we are going to write the augmented matrix corresponding to this system of linear equation, which is 2, minus 1, h, minus 6, 3 and h. So the order of the augmented matrix is 2 by 3. We try to eliminate the x1 variable as usual from the augmented matrix, and we do this row operation on the augmented matrix. 3 times equation 1 plus equation 2 will make the coefficient of the x1 in equation 2 0. Or I will do the same thing 3 times row 1 plus row 2. It's equivalent to this operation which I am doing on the system of linear equation. So the augmented matrix become the second row. There is a change in the second row only, 0 0 k plus 3h. Now we have to conclude, if 3h plus k is not equal to 0, then from this augmented matrix we have an equation like that, 0 equals k plus 3h, which is not 0, as we did in the previous example. So what was the conclusion in our previous example in which we have 0 equals 5 by 2? Of course it's false. So the system of linear equation is inconsistent. So if k plus 3h is not equal to 0 implies the system is inconsistent. We have to find out the values of the h and k for which the system is consistent. So what are the possibilities? That 3h plus k equals 0, and the other possibility is not equal to 0. We have checked that if 3h plus k is not equal to 0, then the system of linear equation will be consistent. So the system of linear equation will be consistent if we have 3h plus k equals 0. Once again I am going to repeat it, that we have checked that if k plus 3h is not equal to 0, then we have such type of equation, some non-zero number equals 0, which is not true. So the system of linear equation will be inconsistent. In order to make the system of linear equation consistent, we should impose the conditions on h and k such that k plus 3h equals 0, which gives us k equals minus 3h. All the real numbers which satisfy this equation, k equals minus 3h, our system has a solution. For example, take h equals 2, then k equals minus 1. This is only one possibility. Then put these values here of h and k, try to solve this one, your system will have a solution. There are infinite many values of h and k satisfying this equation. So we have infinite possibilities of the h and k only the condition is that k plus 3h should be equals 0. That will make the system consistent. We are at the end of our lecture, and at the end of my lecture I will give you some practice problems which I have written on the slides. I'm going to read some of these questions and you will try to solve this one. You can solve these questions. अगर आपको कोई मसला हो, of course you can ask some question via email. Do the lines, these 3 lines, have a common point of intersection? It's the same thing of asking, does the system of linear equation of these 3 linear equations has a solution or not? You have to justify your answer. How you are going to answer this one? You will try to solve the system of linear equation, जो कि हमने आज के लेक्चर में सीखा. आप क्या करेंगे? आप इसका ऑगमेंटेड मैट्रिक्स बनाएंगे. ऑगमेंटेड मैट्रिक्स में वो वाले रो ऑपरेशंस करेंगे that will make the coefficients of x1 0 in the other equations. The second question is, determine the value of h such that the matrix is augmented matrix of a consistent system. This is the augmented matrix of a certain system of 2 by 2 equations. We have to find out the value of h such that the system will become consistent. Okay? We have done such type of example in our today's lecture. So the third question is, determine whether the given system of linear equations are consistent or inconsistent. You have to remember the definitions we have learned in this lecture. A system of linear equation is consistent if it has a unique solution or infinite many solutions. A system of linear equation is inconsistent if the system of linear equation has no solution. So you will try to solve these system of linear equations and you have to conclude that whether the system has a solution, infinite many solutions or no solutions, which will lead you to the categorization of consistent and inconsistent system. Next question is, find an equation involving g, h and k that makes the augmented matrix correspond to a consistent system. Augmented matrix is given. You have to solve the system and find out a relationship between g, h and k, which are real numbers, such that the system of linear equation is consistent. Okay? Inshallah, I will see you in the next lecture. Tab tak ke liye Allah Hafiz.